Okay, so today we will do on a very important topic. Okay, so we'll quantify signal to noise ratio, then decibels, then common mode rejection ratio. That is our objective for today. And we'll take one example, try to quantify everything based on one example. Okay, so that we get a very clear picture. Typically, this is very confusing because of the nuances or subtleties involved. Okay, and these are also studied at different places. Okay, so my idea is to put together all of them together at one place using a simple example. Okay, and quantify all of them. Okay, so that is the objective for the day. The first thing is, so we are going to do dB SNR Cmrr. Okay, so most of this is based on what a Gaussian is. So let me quickly warm up with simple questions on Gaussian distribution. Can anyone tell me this coefficient of a Gaussian or normal distribution? This is coefficient of x minus mu by sigma whole square. Can anyone tell me this coefficient? So this is something that we have done. So I'm expecting you to recall. That is very good. So notice this is going to be 1 by sigma square root of 2 pi or square root of 2 pi sigma square. Most of you got that correct. Very good. Okay. Can we also write down what as, write down the following probabilities? Deviations. So I want 1 sigma plus or minus 1 sigma. Okay. Plus or minus 2 sigma. And then plus or minus 3 sigma. What are corresponding probabilities? It looks like you remember 68.5, 95.5, 99 points on. This is very good. Okay. So you got 68.3. Okay. 0.5 is 0.5 is okay. Percent. This would be 95.5%. This is 99.7%. Quickly recall those. Okay, Anbuchelvan did that. Is this 0.3 or 0.5? We'll just clarify. Okay. Sixty-eight point five or 68.3. .3 is better. Okay, 68.5 approximate. Okay, fine. This we have seen. Yeah, it's good idea to sometimes want to lose marks because of some round of errors or some decimals. Okay, this is very good. I hope others also remember this. Okay, now the second question. This is going to be our example for the day. Okay. So this is 20 millivolt DC signal with, let's say I have 10 millivolt noise. Noise, this is given in RMS values. Root mean square value. Noise kind of keeps oscillating and all that. Okay. So this, if I have to repeat this, so I will write this as 20 millivolt DC. Okay. With 10 millivolt RMS noise. Okay. I'll be writing it like this. Okay, so first question, what is the SNR corresponding to this? What is the SNR? Signal to noise ratio. Let me also write down what this is. This is signal to noise ratio. Then, okay, now Shraddha says 6. Some of you say 2. Okay, notice here we have to be careful about a couple of things. So, signal by noise, this happens to be 20 millivolt by 10 millivolt. Okay, this is 2. But SNR typically given in decibels. Given in dB. And so SNR dB, one has no units. Yeah. So this is SNR in dB. Okay. This happens to be 20 log V signal voltage. So I am writing voltage. Okay. V noise. Notice SNR decibel by definition, actually this is defined based on power. Okay. So if it is written in terms of power, this is going to be 10 log power of signal by power of noise. Okay. So if things are given in terms of watts, you use 10 log, and this base is also sometimes important. So let me put it, this is logarithm to the base 10. Okay. If voltage is given, you are looking at V square by R will be the power. Okay. So you use 20 log 10. So for our example, SNR in dB, SNR in dB equals 20 log 20 millivolt by 10 millivolt. That happens to be log of 2 into 20, that is 6.02 dB. And the intermediary connecting step is this. Okay, this is the definition of SNR. SNR in dB is this, defined in terms of power. Okay, the conversion is this. What happens is, so this will be 10 logarithm to the base 10. If you write power as, power is I square R or V square by R, right? So V sig square by R by V noise square by R, right? This 2 will go to the 2 will go to the front as 20. Okay. So if amplitude of signal is basically, let's say electrical signal, let's take that, voltage or current is given, it's going to be 20 log of the ratio. Okay. Could be SNR of gain also, for example. If power is given, ratio of powers, you do 10 log P6. So let me write it down explicitly. SNR using signal amplitude, amplitude ratio, amplitude ratio. This is 20 log of the ratio. Same thing, SNR using per ratio. Okay. This will be log of ratio. Okay, so contextually you should be either using 20 log or 10 log. Be careful. And your final units, this will be in dB, this will be in dB. Okay, so let's look at our signal again. One more minor question here. Let's say this is 2.1. So the signal we are considering as 20 millivolt DC with 10 millivolt RMS. So now this question is, noise is within plus or minus dash millivolts, 95% of the time. Fill up this dash. RMS is still millivolts, that is root mean square. It is deviation around 0 is 10 millivolts. Root mean square value. What we want is 95% of the time deviation is going to be within this. Can anyone give me the green unknown question mark? So it boils down to understanding what is this. When we say RMS, what is that RMS? root mean square value correspond to? Plus or minus 2, why 2? So let's draw this. Got 0 millivolts, then you got 10 millivolts, minus 10 millivolts. This RMS value is here most of the time. Data is here most of the time. Sometimes the data can also go outside of this. What we want is 95% of the time it is within this. 0.5 is too small, no? It is not too. Noise oscillates in this range. Where is this 2 and 0.5 coming from, by the way? 0.576. So, okay, so let me say this. So by RMS, this is noise. So mean is 0. So squared deviations, right? RMS of noise corresponds to standard deviation. This is centered around 0. Right? And I'm assuming this is typical normal noise. There can be like complicated noise. Normal noise centered around 0. Okay, corresponds to standard deviation. Why? See, notice. So you are looking at a noise value x noise, right? Let's say this is the noise. Okay, the noise data point. Okay, this is already centered around 0. So even if you do a mean, right? So square of that will be just d square. Okay, so this is the average, and that's your RMS as well as that's your standard deviation. Okay, so where your DA is a noise data point. Okay, if it's a time signal, every point you have a specific noise value, amplitude. DA is that noise value. So when we say this is 10 millivolt RMS, we are saying noise distribution has a sigma of 10. Now, based on that, now can you answer this? We know the noise distribution. So let me put this in. Sigma, that is noise distribution, in RMS. So now we know the distribution, we can calculate probabilities. So recognize what is given here, this corresponds to sigma of the noise. And what I'm asking is, what is the probability that, okay, with 95% probability, it should be within this range. So this time you could also or probability. Is still not clear? So sometimes noise value is, this is mostly centered around 0. Okay. The spread in the noise value. Sometimes it can be very extreme also. Sometimes this is plus or minus 5% on either side of standard normal distribution. Yeah. So where does that point correspond to? At least give me an approximate value. Shraddha, your statement is correct. So actually plus or minus 2.5% on either side, because this 95% noise should be within this range. So 2.5% or 5% chance it will be on either side, out of that range. On one side, it's 2.5%. Okay, it's easy. The question is hard. Answer is actually easy if you understand it. Someone other than Shraddha. So again, let me see. Notice RMS of noise. Actually, at least typically the Gaussian noise. Let me add that word. RMS corresponds to standard deviation. Okay, so if you know RMS, we know the standard deviation, we know the distribution, noise distribution. Now we can calculate percentages, ranges, bounds, and all that. Here we want a bound. Noise will be within that bound 95% of the time, or 95% chance that it will be there. Let me give you a clue. Close to one of our landmarks. No, standard deviation is not 95% range. Okay, so let me help either Mugdha or Shraddha. Noise will be within plus or minus 10 millivolts 68.3% of the time. Your noise will be within this range 68.3 percentage. Why? That's a sigma, right? One sigma on either side. Noise will be within that 68.3%. There is, of course, there is a finite chance it will be out of that range, right? So we have quantified it. So noise is within 1 sigma deviation 68.3% of the time. Here they are asking, okay, 95% of the time it should be within what bound, what range? 68.3, this is 10 millivolt on either side. Yeah, this is 2 sigma. That is correct. Two sigma, that would be 20%. Okay. So let me write this down. Answer 95% chance that noise is done sigma, that is 20 millivolt. Do 20 plus or minus 2 sigma. Noise mean is 0. Gaussian mean is 0. Okay, this is Gaussian noise. Noise doesn't have a, unless this is systematic bias, noise mean is always 0. This is, it doesn't have to be explicitly given. Noise is, by definition, this is centered around 0. Okay, so If you put 2 sigma, %95 of the time it will be within 2 sigma, that will be 20 millivolts on either side. There is a 5% chance it will go above, the oscillation will go above 20 millivolts or so. The noise will be like this, okay? One data point, this will be 10 millivolt is here, your 20 millivolt is here, 5% it can actually go above that. Noise, this is oscillating on either side. Okay, so that's your 1 sigma amplitude. I'm showing a time series. This is your 2 sigma amplitude. 5% chance noise can be above that also. This is your 0 mean. Okay, now there is a question, sir, how do we get 8.3 is not the answer. I was trying to illustrate that. You all accepted this, no? RMS tells you what is standard deviation. So what is the chance that, what is a give me a bound so that noise remains within 95%. So if I ask you this way around, okay, noise will be within 20 millivolts. For, what is the what is the probability? You all will say 95.5%, right? Noise will be, the mean is 0. Noise will be within plus or minus 20 millivolts. What is the probability of that? Oh, noise sigma is 10 millivolts. So 2 sigma is 20. So the probability is 95.5. That all of you will answer. The same question I asked other way around. So 95% of the times noise will be within what bound? Give me a bound. Right? So technically you should be able to go from this side to this side. Given the bound, you should be able to calculate the probability. Given the probability, you should be able to calculate the bound. For some reason, this backward arrow is, I know it's slightly harder. This arrow is hard. That is what we did. The forward arrow, mostly all of you, this is straightforward. But given chance, can you find the bound? Essentially, it's the same problem. Okay. So let me also go to that figure. So here I am only plotting noise. The y-axis, I'm plotting, I'm plotting noise. And if this is electrical noise, we are plotting this in millivolts. Okay. So this mark is 10 and this mark is 8. So noise will be like oscillating. It's a time series. Okay. This will be oscillating 95%, 68% of the time it will be within the orange lines. 95% of the time it will be within the green lines. Sense? Mugda, Sadda, Isha. And this value is 0. If it is noise, this mean is 0. And backward arrow is hard. The problem is the same. Okay, give you a bound. What is the probability it will be within that bound? Okay, we can find that. I'll rather give you the probability. Now tell me a bound. Essentially the same problem, but this doing it this way is somewhat not the usual way of thinking. So the students find it hard. And the exact question that we are discussing right now, okay, with a minor changes in number here and there, has shown up as a part of a gate question. Exactly. So I'll tell you what the required probability is. Now give me a bound. This arrow, it was a part of a gate question. Okay, this blue arrow has been a part of a gate question. So what we are doing is very relevant. Okay, so now let's clarify that. Now I am expecting faster answers. Point 2. Same thing. 50 millivolt DC with 10 millivolt RMS noise. Noise is Gaussian, okay, unless and otherwise specified. Okay. The same thing that I asked. So let's ask a couple of quick questions. Point 2. Probability that your noise minus 10 minus 10. What is this probability? Let's make it 30. This probability. Yeah, now all of you are saying it. That is very good. Correct. See, notice this 10 millivolt RMS is your sigma. Okay, what is given as 3 sigma? What is this is 3 sigma, and this is also 3 sigma. Yeah. So it's plus or minus 3 sigma. Now all of you could say this is within plus or minus 3 sigma. Okay, so your answer is 99.7%. Same thing. 99.7% noise is within dash, 99.9% chance or whatever it is. With 99.7% chance, noise is within dash millivolt, plus or minus dash millivolt, right? Millivolt, the answer is of course 30. Yeah, now all of you are getting, I'm very glad. This is the exact question that I also asked here. Noise within plus or minus dash millivolts 95% of the time, or 95% of the probability. Okay, I hope this is now forward arrow 2.2, backward arrow 2.3. That is clear, I suppose. Okay, fine. Now, so we are still at SNR, but we did SNR, we did DB, we also connected that to RMS and bounds. So we did actually using Gaussian, we kind of did these two. Now we have to bring in Cmrr. Okay, so our signal is 20 millivolt DC with 10 millivolt noise. All right. Okay, let's go to that. So your Cmrr, let's define what that is. Okay, this is common mode rejection ratio. Rejection, yeah, this is common mode rejection ratio. Okay, so your CMRR is d log a of gain of signal. If you are processing, your signal has a gain, it affects your signal, it affects your noise. And typically, the effect on signal and noise are different. Okay. Again, let me show you an example. Gain of noise. This is by definition Cmrr. Okay. Where a signal is gain of signal amplitude, and a noise is gain of a noise is the same thing, noise amplitude. I'm saying amplitude because we are not, if it's power, it would be 10. We are talking about amplitude. This is 20. Let me also highlight that point. Because we are talking about amplitudes, that is 20. This is your CMMR and this is in dB. CMMR in dB. Okay. In decibels, your CMMR is this. So now let's look at an example of this. CMRR example. So your 20 millivolt DC with 10 millivolt MS. Nice. Doing some kind of processing. So the processing, what happens is that becomes 40 millivolt DC with 0.2 millivolt MS noise. Whatever processing you did, it affected signal, it also affected your noise, but it affected it differently. Okay, so calculate CMRR. Calculate CMRR in dB for above processing. Okay, so often you could also say that noise is a common mode. This is often this is noise. Okay, what you get in say if you are trying to find difference in ECG leads and all that, common thing happens to be the noise. Okay, so calculate CMMR and dB for above processing. Let me also write down. Okay, you are given you the signal input that becomes this. So let me also write this explicitly. So after processing became this. After processing, it became that. Sort of again, let me leave you some hints. So this is your input, and this is your output. by definition of CMMR is this. CMRR, sorry, is 20 log A signal, gain in signal by gain in noise. Let's do one bit at a time. Okay, so A difference, I suppose A difference you are referring to. So gain in signal, let me do one. Gain in signal. This happens to be 40 by 20. That is 2. Millivolt will cancel. That's very good. What is a gain in noise? Millivolt became, sigma became that. Okay. Now, gain in noise, okay, or common mode, that I have written it as A noise. Okay. Put is 0.2. Input is 10. 0.02. See, notice the processing you're doing, some nice things are happening. Your signal is getting better. Your noise is also getting better. Noise is getting weaker. Signal is getting stronger. Okay? And your CMMR tells you how good your processing is. So it proportional to how signal improves. It's inversely proportional to how noise improves, or noise amplitude decreases. Okay, but in fact you could just go ahead and calculate it. So CMRR equals 20 log of 2 by 0.02. Happens to be divided by 0.02. Log answer is 2 into 20, that's 40. Great. We're getting, so this is CMMR is expressed in decibels, so this is 20 log of that ratio. This is 40 decibels. Many of you, or Vaishali there, Abhijay, many of you are typing this. Okay, this is extremely important. This simple example, okay, often shows up as a 2-mark question. Great. Now, let's add some spice. And we still have 15 minutes, right? That's a lot of time. Okay. Above example, was SNR input, SNR output, CMRR related. Everything in decibels so that sometimes you can easy to later. So let's go ahead. So 20 millivolt, we found the SNR. SNR was 6, I suppose. For the input, V sig by V noise 20 by 10, that happens to be 6 decibels. Okay. So let me write it down. We have already found this. SNR of input equals 6 decibels. Cmrr, we just calculated, that happens to be 40 decibels. SNR out, okay, that's as a ratio. So I'm using dB. Okay, let's highlight that because in dB everything will be you're adding or subtracting, and calculations typically you're doing in dB. So what is your SNR input? So one is, if you know the relation, you can calculate that, or you know the signal, right? You know the output 40 millimolt at 0.2 millivolt RMS. So just calculate the SNR out. This happens to be T log 40 by 0.2. How much is this? 40 divided by 0.2 log of answer into 20. 46 dB. So now what is going on in dB? Can you see the relation? See, notice at the end of the day, your output SNR has increased. Your signal is better now. That is very good. Input SNR was weak. What is the CMR? What is the processing doing? So how are the three related? Let's make it, how are SNR input, SNR output, CMRR are related? So in dB, SNR output is SNR input plus CMRR. Yeah, this is in dB. You are all talking about the ratio, right? Ratio becomes addition, subtraction in decibels. When you take log, they get added up. Many of you are mentioning that's correct. Notice many of you are saying SNR out by SNR in, that is CMMR. Yeah, that is correct, right? So if you're dealing with in decibels, things just get added up. So this is, now things are additive. This is the reason we move to a logarithmic scale. So in this case, the processing is certainly improving. In this case, in the above example, processing is good. The above example, processing is good. Whatever processing that happened was good. Processing is good. How do you know that? There is an improvement. is an improvement. We could also just look at the signal noise, say that a 20 become 40, signal becomes stronger, noise became weaker. But it's better quantified this way. Okay, now this also all of you got. Then last thing. This is called signal averaging. This is one processing that you do. If you average signal, signal remains, information remains, noise tend to cancel each other. This is not root mean square average. This is just average. Noise tends to get cancelled. By default, this is simple averaging. Noise tends to get cancelled. Not squaring noise and averaging them. It's just averaging noise. Okay, tends to get cancelled. Okay, or get reduced. And when does it happen? Averaging multiple signal, multiple data of same signal, while averaging multiple data of same signal, multiple data of same signal. That is, you take a ECG signal, you take it not once, you take it 10 times. Sometimes you take it 100 times, right? Of same signal. Noise tends to get cancelled, get reduced. Okay. And how much can we quantify this? How much? That's a fair question that we can ask. Yeah, now even before I say this, some of you are saying, notice noise upon averaging this becomes, it depends on the number of data points that you are using. Noise becomes noise over square root of n. Standard deviation becomes 1 by root n. Okay, so let me again put this in English. That is noise sigma, it is 10 millivolts, increases by a factor of 1 by square root of 10 using 10 signals. 1 by square root of 10 is a fraction, right? So it decreases using 10 samples. You average 10 samples, it becomes by square root of. You average 50 samples, it becomes 1 by square root of 50, and so on. Now let's go back to the processing that we showed. Millivolt RMS became 0.2 millivolt RMS. This processing involved signal averaging. So to reduce noise, say you did signal averaging. how many points do you need? Okay, example. So this, in the side we have 10 millivolt RMS noise, average using n samples, it became 0.2 millivolt RMS noise. What is n? You find the number of samples used to average, so that this conversion happened. We are also on time, so this is the last question, and there is one more minor detail. I'll point that out, and then cannot have noise. I can also is what noise amplitude. Okay, use, notice 10 noise reduces by a factor of 1 by square root of 10. So here you have to use, again, this forward problem is fairly easy, right? Say if we had used 50 samples, 10 millivolt would have become square root of 50, 7.07. One divided answer is 0.14. So 10 would have become 1.4 millivolts. Now 10 is becoming 0.2 millivolts. How many samples? Okay, in the forward backward arrow issue. Given this, so decrease by a factor of, given number of samples, calculating the factor is easy. Given number of samples, calculating the factor is easy. Now we are technically given information to find the factor, how much it reduced. Find how much is the sample. Root n is 50. Okay, root n is 50. So what is n? Oh, what is n? What is the number of samples? Number of samples is 2500. Okay. So number of samples n equals root n. So let me again, some of you are wondering, okay, how do you do this? At least, put this in simple English, retain this in simple English. Okay. Noise reduced by a factor of how much did it reduce? By 0.2. reduced by a factor of 50. Is reduced by a factor of 50. Okay. Definition, this corresponds to root 10. Okay. This corresponds to 1 by 50. It reduced, this reduced by a factor, right? So this is 1 by 50. That corresponds to root 10. And that implies your n is 2000. Your n is 50 square. Okay. 2500. Again, this English holds good. Noise reduced by a factor of 10 by 0.2, that is 50. So noise became 1 by 50. That should technically, that factor corresponds to 1 by square root of it. So let's quickly recap. Noise is typically defined based on Gaussian distribution. So knowing this bounds is useful because you can now, given bound, you can tell probability, given probability, you can give bounds. That is point number 1. You can quantify SNR. SNR typically quantified in dB. Okay. It is 10 log power ratio. If voltage is given or current is given, 20 log voltage ratio, 20 log current ratio. That's point number 1. And then given bound, you can calculate probability. Given probability, you can calculate bound. Cmrr is 20 log ratio of gains, signal gain by noise gain, or common mode gain. Noise is to common mode. Okay. So in this example, we calculated common mode rejection ratio, and the 3 should be related. Output SNR plus CMMR should give you output SNR. CMMR should be SNR output minus SNR input. That is one thing. And then one way this thing reduces, one typical processing we do is, say, notice to increase the gain, you could do a op amp. Let's say 20 to 40, you can put a op amp or something like that. While you put an op amp, the 10 millivolt also tends to get amplified. That's why you use a instrumentation amplifier, right, to reject common mode noise. Okay. But on top of that, either say the instrumentation amplifier does this. That is one way to do this. Okay. Or if you just look at noise, one way to reduce noise is just to average them. When you average n samples, noise amplitude reduces by 1 by square root of n. And so the last, not a question, last subtle detail, I told you 50 millivolt DC signal. Same thing, this is, they are referring to AC signal, they are 20 millivolt peak AC. Okay. So in terms of AC, be careful whether they are giving peak or amplitude. Okay. Just write that down. 6, the last one. No questions, just note. 20 millivolt AC signal responds to 20 into 1 by root 2 millivolt ms. This is for signal. And typically, so this is presumably the peak is given. be careful. Don't take the peak and do calculations. Take the RMS and do, say, SNR calculation, Cmrr, any calculation that we did. Be careful about this. So technically, that is 20 root 2 is 1.414. Yeah, notice this. Actually, if they give you 20 millivolt AC signal, that should correspond to 14.414 millivolt amplitude. Be careful if you are dealing with AC or RC. Thing we discussed applies. In DC, the RMS is the amplitude. So no confusion there. If it is AC, you have to deal with it carefully. Okay, great. So with this one thing, I wanted to give simple examples on all this SNR, DP, CMMR. Okay, we have this, and idea is, so now we have simple illustration. You can, one example, you can quantify all these parameters, and typically every year there is one question from this. Okay, the way they ask it differs. Okay, they can ask this in either one of the parts that we one of the questions here, say question number 3 itself is a question sometime. Okay, 2 itself is a part of a question. Things like it shows up in different forms, but from what we discussed, one question shows up. Okay, every year. Okay, with that, let's stop.